So let us look at one more example 3. Okay, that's very interesting. I don't know whether I discussed the popcorn function. No? Okay, let us discuss what is the popcorn function. So f is a function on 0, 1 to r, and this function is f of x is equal to 0 if x is irrational like before. In 0, 1, if it is irrational, the value is 0. If it is a rational, it will be a fraction, p by q, right? If it is p by q, where p and q, this is a number between 0 and 1, so q will be bigger than p anyway, right? Because it is between 0 and 1. So put it as 1 over q if x is p by q. Forget the numerator, take only the denominator of that function. Okay? Clear what is the function? Can you think of drawing a sort of a graph of this function? What do you think the graph should look like? So let us try to plot this to see whether we can do something or not. So this is 0, 1, function will take values between 0 and 1 only, right? What is the, okay, let us see when it is 0, this is not defined, right? P by q, denominator could be anything. So let us say or x is equal to 0. Both for x equal to 0 the value is 0. For every irrational the value also is. So what is the or you can put the value at 1 also 0 if you like, doesn't matter much actually. So let us take what is the value at the point x is equal to half. When x is equal to half, what is the value of the function? It is half, right? Is rational, the value is half. Okay. It is 1 by 3, what is the value? Value is 1 by 3. What is the value at 2 by 3? Again forget, so again the value is, so this is 1 by 3, this is 1 by 2. So now you can see what is happening. At 1 by 4, what is the value at 1 by 4? 1 by 4. At 3 by 4 is 1 by 4. So here is 1 by 4. So value at 1 by 4 and 3 by 4 and so on value. So it will be kind of triangular kind of a thing, right? And here the value is smaller. So if you make these dots bigger and smaller, these are smaller, just for the sake of visualization, they look like popcorns when being fried or baked. They are jumping up, right? So this is normally called popcorn function. In fact, it was given by a mathematician called Thomas. I think spellings I am not very sure. Thomas function or popcorn function. Anyway, it doesn't matter. Mathematically, we know what is this kind of a function. Do you think it is a continuous function? No, it doesn't look like. Otherwise, I should have drawn the graph better. Right, but what are the points of discontinuity of this function? at what points it is discontinuous. Right. So let us look at the way of analyzing discontinuity would be, because the function is defined differently at a rational, differently at a irrational, right? So we should analyze continuity in two cases, when x is rational and is irrational. Supposing x is irrational, the value of the function is 0, and look at a sequence, right, of points converging to that irrational. But the sequence I can choose of irrationals, then all the values will be 0, so no problem. But I can choose a sequence of rationals converging to that irrational. And if I choose the rationals, then close to it I can have a point where the value is not 0. So that will not converge to 0. So at all irrational points it is discontinuous. At all irrational points it is discontinuous or continuous? Are you sure? Yes? Okay. So let me analyze discontinuities of f. I have given you some idea, right? Now supposing let us take x to be a rational point, the value will be 1 by q, right? Now value at all rational points is 0, right? So now given a rational point, so here is a rational point, here is 0, here is 1, this is a rational point, call it x0. I know the value is not 0 for the function at this point, right? But I can have a sequence of rationals converging to it, irrationals converging to it. Irrationals are dense. Irrationals are dense, right? So I can have a sequence of irrationals converging to x naught, but the value at every irrational is 0. But the value of the function at that point is not 0. So at a rational point it is not continuous. So that's why I was saying, try to convince yourself that this function has discontinuity at all rational points, it is continuous at all irrational points. At a rational it is discontinuous, is that clear? Right? If you want to say it is discontinuous everywhere, no, it is not. Rationals are the only points of discontinuity. So exercise, okay, so exercise. I have already given you that at a rational point as it is discontinuous, right? That these are the only points. That means what? That means at every irrational point the function should be continuous, okay? So check that. So mull it over and think about it. I will put it as a problem in the problem session, ask them to discuss it with you, that this is so. Let us not discuss now, okay, because we will have time to think. Let everybody have a time to think about the problem and discuss in the problem session. That is a better way of doing it. So anyway, the number of discontinuities of this function are infinite, right? Rationals, and every subinterval of 0, 1 will have an infinite number of rationals, so infinite number of discontinuities. It has infinite number of discontinuities in every subinterval of 0, 1, right? Now let us try to understand, is this function f integrable? Is this function integrable, right? Obviously it is not differentiable everywhere anyway, because it is not continuous everywhere, so that point is okay. Let us say integrable. Can I think of saying what is the graph, what is the area below the graph of the function? So let us try to see. So to do that, so let us take P a partition. So if I want to show it is integrable, what I should try to do? Let P be a partition of AB, 0, 1. What is the lower sum with respect to? I have to compute lower sums and upper sums, right? What is the lower sum? That will be 0, because every subinterval will have a irrational in it, so it is 0 for every partition. I have to worry about what is the upper part, right? Okay, so let us try to see the upper one. Upper sum, the contributions will come from the rational points, because at rationals the value will be non-zero, 1 over q into the length of the interval, right? So I have to bother about at how many points the function, what value it takes. So let us look at the set A. So let us, if I want to show it is integrable, I have to make upper minus the lower small for some partition, right? Okay. So let us start with, let epsilon be given. So I am looking at the values of the function. I want to look at, here is my epsilon. At how many points the value can go above epsilon? At how many points in the domain the value of the function can go above epsilon? So those are the rational points, and at the rational points the value is 1 over q. So the only points possible are when 1 over q is bigger than epsilon, right? So I am looking at the set. Consider A to be all x belonging to 0, 1 such that the value of f of x is bigger than or equal to, doesn't matter, epsilon, right? What can you say about A? It is bigger than, f of x is bigger than epsilon when f of x is 1 over q. So how many q's are possible so that 1 over q is bigger than? Countably many? I don't know, I am asking. So x belonging to A, f of x not equal to 0 implies f of x is equal to 1 over q, right? So we want 1 over q bigger than epsilon, that is q is bigger than 1 over epsilon. No, other way around, q is less than, good. Q is less than 1 over. How many q's are possible between 0 and, q has to be bigger than 0 anyway, right? Between 0 and bigger than 0 and less than, epsilon is fixed. How many are possible? There are only finitely many, not countable, only finitely many, right? Q is positive. So how many are possible? Only how many natural numbers bigger than, so A is, so that means implies A is finite. So the set of points where it goes above, so points where it is less goes above, it is only finite, right? So let us call this finite number as something, say x1 less than x2 less than finite some number, say xn, okay, bigger than a, less than, okay. Now, so here is a point xi. At this point the value goes above epsilon, right? So I want to make them, in some sense I want to enclose them in a box so that these points are inside intervals of length small. So around every point I can have an interval, so it is x1, x2, xi and so on. I can enclose each one of them in a interval, right, so that total length of these intervals is small. There are only finitely many, right? There are only finitely many. So let us put, so enclose these points in intervals of total length small. So meaning what? This is all English. What is the mathematics of that? Right? That means for every I find a interval I, an interval such that xi belongs to I, length of I is small, sigma length of I equal to 1 to n is small. So how small you want it? Let us make it less than epsilon again. Is that okay? Around every point find an interval, right, of length epsilon by n. So when you add up all this finite number, total length will be epsilon by n plus epsilon by n times, that will be epsilon. Okay, here is my A and here is my B. Okay. Now these intervals have got some endpoints like this. These are the points. So these points give me a partition of the interval AB. Right. So what are the partition points? A, one point here, next point here, next point here, next point here, and so on. Okay. So if you want, let us give them a name. So let us, if you like, so let I be, you want to give a name. So let us AI, BI. So what does it look like? Here is A1, here is B1, here is A2, here is B2. X1 is somewhere inside, X2 is somewhere inside, and so on. Xn, AN, Bn, and here is A, here is B. That is the picture it looks like. Length of A1, B1 plus length of this plus length of this put together is less than epsilon, right? So this gives me a partition. So consider this partition. So what is this partition? So P is A equal to A0 less than A1 less than B1 less than A2 less than so on less than AN, Bn less than B, right? With respect to this partition, lower sum is 0, we know that always. Lower sum for every partition is 0. I want to calculate what is the upper sum with respect to this partition, right? So the upper sum I will divide it into two parts over the intervals which are a1, b1, a2, b2, an, bn, right. What is upper sums? Maximum value in a sub-interval times the length of the sub-interval, right. So, let us divide it into two parts. So, one part is with respect to this ai, bi's, okay. So, let me call it as maximum value in ai, bi. So, length is length of ii, right, okay. I equal to 1 to n plus the other parts. So, these intervals. So, what is this? Sigma, let us call it mj if you like. So, what will be the length now? It will be a2 minus a1, a3 minus, right. So, it is an minus b n minus 1, what should I write, n minus 1 b1, okay. Just a only way of writing. So, this we called it as a0 and this we called it as bn plus 1. Then what I am looking at is, so a1 minus is, okay. Is that okay? Over j. You understand what I am writing here? I am writing over the sums over these green portions. So, what will be that? The maximum value mj, whatever that may be, into the length of the interval. So, length of the interval will be like, here it will be an minus, right, a2 minus, what is the length here? a2 minus b1, the length next one will be a3 minus b2. So, that is what I have written here. Oh sorry, aj, yes, aj, okay. Now, in the red ones, I do not know what is the value of the function, right, but I can cite the red ones, I can write some constant m, the function is bounded, right, bounded by 1 into sigma length of ii, all the intervals, maximum value, each mi, the maximum in the sub interval is less than or equal to maximum in the whole interval, right, plus what can you say about the other part? mj, what is the mj here? That is the maximum in the portion where the green ones. What is the value of the function in the green portions? In the red ones, the value was bigger than epsilon. So, green ones, those points where it is bigger, there are finitely many. So, it will be less than epsilon, right. So, let us write this value is less than epsilon times sigma aj minus bj minus 1, whatever that j may be. And this length, this one, we have seen it is the way we found these intervals were less than epsilon. So, let me put that as epsilon. So, less than or equal to m times epsilon plus epsilon times some, call it as m1. This is a constant, okay. So, total length, so is less than or equal to m plus m1 times epsilon. So, the basic idea of the proof, so I have found a partition, say that the upper sum is less than epsilon times a constant. So, the constant does not matter in our analysis. So I have found a partition so that the upper sum, lower sum is 0, so that the difference is less than epsilon. That means the function is integrable. So let me revise a bit the idea of the proof. See, this is the crux of the proof. Says upper sum will arise from the values where the values are non-zero, right? So where the values are non-zero, I look at those points where the values exceed epsilon and less than or equal to epsilon. Where they exceed epsilon, the value of the function, there are only finitely many such points. Those points where the value can tend to become larger, I enclose them into small intervals of total length small. So that upper sum with respect to those intervals, I make it small by enclosing each point in a small interval of total length small. In the other intervals, the value of the function itself is small, so it doesn't matter because the total length of the subintervals is b minus a. So that is how I contain the upper sum minus the lower sum. I make it small by making the upper sum small in the intervals where the value exceeds something. There are only finitely many. Other parts doesn't matter if the value is less. So this is try to read the understand this proof yourself later on when I will send you the slides. The basic idea is that this function is a function which has got discontinuities infinite in every subinterval, but still it is a integrable function. The earlier function rational, irrational, 0, 1, that was discontinuous everywhere. So that was not integrable, right? And if the number of discontinuities are finite, that is not really a problem, right? Once again we can define the integral in separate parts and add. So the function is integrable. So integrability of the function has to do something with continuity of the function. We have got different examples. Constant functions, continuous everywhere, integrable. Monotone function, discontinuities are countably infinite at the most. We don't know how many, but still integrable. This function is a function with infinite discontinuities in every subinterval, still integrable. And the other extreme is that 0, 1 function, discontinuous everywhere and not integrable. So somewhere continuity, we have to say how many points you are allowing discontinuity for the function to be integrable. So next time we will prove first one theorem that every continuous function is integrable. Like every monotone function is integrable, every continuous function is also integrable. And there is a deep theorem which says you can actually give a measure of how many discontinuities are allowed. And that is the beginning of a story called Lebesgue measure. That is the beginning of the probability theory, Lebesgue measure, measure theory, and so on. That basically says the set of discontinuities of a function, if they don't contribute much in the length of the interval, then that function is going to be integrable. For example, for a finite set, in this we were able to enclose each finite set in an interval total length small, right? But if I take a countable set, even that I can enclose each point in an interval of total length small. For example, x1, x2, xn is a countable infinite set. x1 enclosed in an interval of length epsilon by 2. x2 enclosed it in an interval of length epsilon by 2 square. Next one epsilon by 2 cube. So what is the total length of these intervals? Sigma epsilon by 2 to the power n, and that is a geometric series. The sum is equal to epsilon. So you can enclose countable infinite set of points in small intervals of total length small. So in that sense, you say that the countable set don't contribute anything towards the size of the interval. You say it is countable number of points form a set of length 0, because you can put them in any small collection of subintervals. So there is a deep theorem says that a function is integrable if and only if set of discontinuities are small size, set of length 0. Okay, will not prove that theorem. I am just saying this may come across sometime somewhere. But you have seen a lot of examples of that, right? On one hand, continuous everywhere, right? Constant function, slowly we are coming to monotone, infinite but integrable, right? Then this function, popcorn function, infinite in every subinterval, still integrable, and then discontinuous everywhere, not integrable, right? So let us stop here.